Thank you very much for the opportunity to speak here. All I'm going to be talking about is ongoing joint work with Charles Bordenave. And the very rough outline of my talk will be to try to compare something called something I will call the local spectral radius of a graphing to its global spectral radius. And kind of the point will be that in general there is no way to say something about the two, like any relationship between the two. But in the very special case of unimodular Galton-Watson trees, we can actually show that the two are the same, and this will have consequences for finite random graphs as well. So this is the very rough outline, and I want to say that I really encourage you to ask questions. The more you interrupt me, the less nervous I will become. So please do that. And I've already said the results of this talk. You all understand it, right? So there is no way I cannot state the results. I'm not worried to not make it to the end. So please interrupt me. But to be just a little bit more specific, I want to start out with the graphing G. What that means for me is, it's a graph. It has some vertex set, edge set, and some measure on the vertices. We've seen them a lot last week. I won't go into many details, but the way I imagine it is that there is this measurable space of vertices, and I'm allowed, since there is this probability measure mu living here, I'm allowed to pick vertices of my space at random. And if I do that, so I pick X in here, then I can associate to it its connected component, and I think about it as a rooted graph at this vertex. So the picture is that maybe it starts to look like a tree. Later on, there might be cycles, whatever. But this is a countable graph, and if X is the point I picked, then it comes with a very natural choice of root, which is this X. And so if I do this randomly, then this will be a random rooted graph, and the probability measure preserving property of the graphing will get translated to what is called unimodularity of this random rooted graph. This is a technical thing. You can just think about it as the PMP condition here. I won't define it, but I will try to follow Sam in the sense that most of the time I will denote it by GO. So calligraphic G is the graphing, and then GO is a random rooted graph with the probabilist notation. So this is a random variable which takes its values in the space of rooted graphs. Okay. And so when I talk about local and global spectral radius, I will be thinking about this as the local information and this as the global graph. So what do I mean by local spectral gap? Spectral radius, rather. So what's local spectral radius? So the natural space to work with, if I have this countable connected component, it's the little L2 space of the vertices of G. And I have a Markov operator here. So M will be my Markov operator. Markov operator simply stands for whatever the simple random walk does, but just to be on the safe side, this is what it does to a function on the L2 space. So if I look at how it acts on F and evaluate at a vertex V, well, that will be just the average. So I have to look at all neighbors of V. I have to add up the values, and then in the end, I have to divide by the degree of the vertex V where I'm averaging. So this really just looks at the neighbors, takes in the values, and averages them. And when I say spectral radius, then what I really mean, so I will denote it by rho of GO. This is nothing else than the L2 norm of this Markov operator. Any questions about this so far?
Wait, sorry, it's not a self-adjoint operator, yeah?
Yes, very good. I was trying to avoid this, but really this comes together with the, so here it would be natural to look at the counting measure, but the counting measure is not stationary. If you're in an irregular case, then you have to rebias by your degree compared to the expected degree. You write that P there, now it's self-adjoint, so now it makes sense.
Yeah, because you define the spectral radius already as the norm, like, or just above.
Point is, write the pi there and you're fine. Okay. Yes, it's an important comment, but not important for our purposes. Okay, any other questions? This was a very valid question. I was just trying to put it under the rug.
Really need two norms?
Yes. Okay, so what do I mean by global spectral radius? So it will be very similar, but not exactly. So if I'm trying to define the same thing here on this G, then the natural place to work on is the big L2 of the vertex set of G. And since this was pointed out, I don't want to take the measure mu, but rather a rebiased version, which is again the same rebiasing with the degree compared to the expected degree. So this is where I'm acting, and now I will use calligraphic M for the Markov operator. And then, of course, the definition of the Markov operator is the same, exactly the same characters. But the way you should imagine it, it's acting on the whole of the space at once. And if I look at this thing, then it's kind of obvious that the constant one function on the vertex set is always an eigenvector.
Once again, say what's mu prime is. I know you want to avoid that.
Mu prime?
Yeah.
It's mu biased by the degree of vertices.
What is it?
That means that d mu prime divided by d mu at a vertex v is the degree of v divided by the expected degree when expected with respect to mu. Does that make sense?
Yes.
Okay. So higher degree vertices get more mass. And I want to point out a remark I made earlier. So this really is the stationary measure under the random walk. So if you take this measure, randomize a point, take a step with the simple random walk, you will be still seeing a random point with respect to this mu prime. Okay.
Forgive my ignorance. So
no problem.
You mean Hilbert-Schmidt norm? I mean, that's usually two norm for an operator refers to in the Hilbert-Schmidt operator. So maybe can you explicitly write what norm, the definition of the norm you're using? Operator norm is usually infinity, is what you, or maybe in different communities.
I'm a bit unsure, but the point is that this will be. So this is for the countable object. This is nothing else than maybe 2n root of the probability of return to.
Okay.
So for the countable object, this is just the exponential decay rate of the return probability. And non-amenability is simply if this is 1 or not, which will come up in a second. Okay, so but I want to point out is that here, this being 1 or not is exactly non-amenability. But here, if I just said I want to look at the 2 norm of this, it would be always 1 because there is always a trivial eigenvector with eigenvalue 1. Okay, so just as in finite graphs, there is always a trivial eigenvector. So if I want to talk about spectral radius, then I really should get rid of that. How do I do that? I say that, okay, I look at those functions in this space which average to 0, which is really nothing else than the orthogonal complement of my trivial eigenvector, and then I define the spectral radius of calligraphic G to be again the norm, but restricted to this L20 space.
That's you ask for questions, so yeah. Okay, so here this pi, it's also non-invariant, it's the stationary guy. Don't
Yes.
you want to put weight like FU?
So the direct product in this space is some FV times GV times pi of V. So
No, I'm saying in the Markov operator, don't you want to take a weighted average? Even though your points are weighted by pi?
yes,
Are you saying it's reflected in the inner product?
it's reflected in the inner product. And
Oh, I see, so it's take, I see, okay. And so it's same here, I guess.
yes, so the inner product, in the inner product, this thing shows up, but in the definition of averaging, it's not. Averaging is really just averaging. It's just you look at your neighbors and you average up what you see. That's very combinatory. And but the picture I want you to take away from this is that the local graph, it really works as in this countable world. So you know, this being one or not, it's really amenability, non-amenability, and then the graphing itself, it works like a finite graph. There is always a trivial thing. You have to get rid of that. You're looking at the second largest eigenvalue of a finite graph. Okay.
For the local amenability, you mean like you know, cheaper constant amenability for like the.
Well, this is Kesten's theorem, if you like.
Yeah, right.
Yes.
It doesn't mean that your graph is a.
No. I mean, it just says something about a local component, right? And the thing I'm kind of looking at, the question I'm about to ask, or that I'm asking in general, of course, is can you relate local non-amenability to anything global? And so the first result, which is, I guess, kind of folklore. So if you have a group, you know, maybe finitely generated, non-amenable. So what non-amenable in this case means that this is less than 1. Then, well, you can look at its Bernoulli shift, or rather the graph you get by looking at gamma acting on its Bernoulli shift. So I have gamma acting on the Bernoulli shift, and then you can look at the Schreier graph of this action with respect to this set of generators. That's what I mean by the graph of the Bernoulli graphing in this case. And so this will be my calligraphic G. And then in this case, it's kind of well understood that the local one is actually equal to the global one. I don't specify the root because in a calligraph it doesn't matter. Okay? But this is already a non-trivial statement. It says that if you have local expansion, then you have global expansion. And the usual way to prove this is through representation theory. So you can argue that this L20 decomposes as countably many copies of the regular representation, maybe some quotients if there is torsion, but there is something to prove here. That's the first remark I want to make. And the second remark I want to make at this point, I think this is a very good point. Like, why do we care? Why do we care for such a result? And the answer is that having, so in this case, this is less than 1. So I can prove that this way I can see that this global spectral gap is less than 1. And just like as in finite graphs, spectral gap gives me control over expansion. So this graphing will be an expander, and then I can start to play combinatorics games on it. Like, for example, the Lyons-Nazarov result, which was mentioned many times last week, it explicitly relies on this, because factor of IID stuff converging somehow, in their case, relies on the fact that this Bernoulli graphing is an expander. Okay. Any other questions about this? Okay, so if not, then I'll go on and just mention that, of course, if I didn't look at Bernoulli graphings, then there would be no hope for such a statement, because already non-amenable group can have actions that are not strongly ergodic, and if it's not strongly ergodic, then it cannot have expansion, so no spectral gap. I'm just putting big words after each other, but my point is that really for non-Bernoulli, this question is maybe interesting, but not very approachable in any generality. But the next result I want to tell you about is by Ági Backhaus and Balázs Szegedi and Bálint Virág. So they do the same thing. So it's the same, but for the irregular tree. Now, why do I mention this? Because, you know, it seems obvious, right? This is a Cayley graph, but they do it without any colors, and that's a slight nuance here. So here, this really, when I think about the Cayley graph of gamma, then it comes together with a decoration by the generators. There's orientation, and that's how the representation theory thing works. Here, there is no group action at all. And you could, same for TD, and it's Bernoulli graphing. So, you know, Bernoulli graphing is not so obvious to define in this setting because there is no group action, but it's something you can do. It is really the analog of the Bernoulli shift. The way you should think about it is that you take random colorings of TD and you connect two of them, random labelings of TD, and you connect two of them if one can be moved to the other, if moving the root to a neighbor in one of them produces the other one with this labeling. So you can, by the way, and we will in a second do this for an arbitrarily unimodular random graph. Okay, so
yeah,
yes.
so this is the same meaning. So the two.
Yeah, the two are the same.
Are the same.
Yes.
And is TD as general as they showed, or is this something?
This is the way they stated it, but I think it's unimodular transitive graph. It extends. So, but transitive is important.
Yeah.
And a couple of years ago, together with Ferry Bench and Aranka, who is here, and myself. So we did the same for well, not the same. So maybe I'll state it properly. So if we have GO, which is a quasi-transitive unimodular random graph, URG stands for unimodular random graph, and we know that the local one is less than 1, then we can show that, and G again stands for the Bernoulli graphing. From now on, always Bernoulli graphing. Then then this is less than 1, but not necessarily. Quasi-transitive just means that there are finitely many different orbits of the automorphism group. This is so this is or at the time it was a non-obvious generalization of this reasoning, and we need it for a very specific reason to actually show some, as I mentioned, some perfect matching thing. But it made us ask the question in this paper. We asked whether this is true for any unimodular random rooted graph, right? It's very natural to ask. You know, can you drop this quasi-transitive assumption? And then in a couple of months, Nikolai like that. So he came up with a counterexample. So example of a unimodular random graph such that the first thing is less than 1, but the second thing is equal to 1. Okay. Yes.
The second one always either or equal to the.
Yes. I didn't say that. So this being at least this is obvious. It's the easy direction all the time. and Ramanujan would be the two things being the same. I'll come to that in a second. So in a sense, this is a Ramanujan statement, and that is a Ramanujan statement, and this thing is not a Ramanujan statement.
Question is,
Yes?
I mean, maybe I misunderstand, but aren't the second one being one is saying there's no spectral gap.
Yes?
So I feel like there are lots of examples that are already known in the literature of this.
I'm not exactly sure. So this is not very hard, but at least it wasn't an obvious thing around where we asked, and it took a few months until Nikolai just gave us the example. Maybe this is very well understood. Right? I'm not claiming that. What I claim to be interesting is the following. So the result we have now with Charles, or Charles rather, is that we can, so this is Bordenave, myself. So what we can prove is that if we start with a unimodular Galton-Watson tree, this stands for Galton-Watson, then so the Bernoulli, the spectral gap of the Bernoulli graphing is equal to the spectral gap of TO if the minimal degree of this Galton, I'll say in a second what unimodular Galton-Watson tree means, but it's a random tree. And if the minimum degree is at least 5, then we can prove this. And in case the minimum degree is equal to 4, then we can show that it's almost true. So there is a factor we lose 1.002. And in case the min degree is equal to 3, then the factor is 1.007. So it's close, but not quite. But if the minimum degree is at least 5, then we're home. So I guess I owe you at least a definition of what a unimodular Galton-Watson tree is. So here's the definition. You start from a root, and it will have a random number of children. It will have d children with some probability PD. And then if I didn't insist on this unimodularity, I would just tell you that every other vertex will have d children with probability PD. But I can't do that because then it won't be unimodular. Then the root will behave differently to the others because everyone later will have one more edge than the root in distribution. So what I have to tell you is that the probability later on to have d-1 children has to be some QD, which is not very surprisingly, it's again a rebiased version. So d times PD over the expected degree. But everyone later, so only the root has this special PD, everywhere else it's the same distribution. This is the probability QD, and with this probability you have d-1 children. And now with this rebiasing, I managed to make it such that if I look at this graph from here or from here, I see the same thing in distribution. Okay. So this is the object. It's kind of if you like, it's a random relaxation of a regular graph, but it behaves very differently. So to prove this is much more difficult than the regular graph. So this is a good point to ask you to ask questions.
I have a general question.
Yes.
So in the group theoretic context, decomposing the Friedman representation to the regular representation, you get a lot more information about comparing the two Markov operators than just a spectral radius, right? I mean, you get like spectral.
Okay.
Is anything similar hold here, or is it really just all about spectral radius in these more graph theoretic situations?
I don't know, but I guess the argument that they gave, and which we work very hard to extend here, I don't think it gives you on the nose any further information. Maybe if you're very smart enough, you can push the representation theoretic proof somehow, and maybe you can get that. That's an interesting thing to do, but I don't know on the nose how to do this.
Radius is the most important.
Sorry?
The radius is the most important part anyways.
I mean, but so, yeah, sure. But what I mean to say now, I guess I have a couple of minutes. I do have a couple of minutes, right?
2 minutes, yeah.
Good. So, so what I want to say is that this result helps us prove, helps us extend an important theorem in finite random graphs. So there is this important theorem of Friedman, I think it's from 08, which says that that random irregular graphs are almost Ramanujan. So what I mean by that, so I will denote by Gn. It's a finite graph on n vertices, it's deregular, and among such things, it's chosen randomly. And then I look at its spectral radius, by which I mean the second largest eigenvalue in expectation. And I look at if it's bigger than the spectral radius of the deregular tree, which is just this 2 times square root of d minus 1 over d. And actually, since the statement only says almost Ramanujan, I have to add an epsilon. And then I can look at the probability of this happening. And the statement is that this goes to 0. And this should hold for any epsilon error that you might want. Okay, so let's see if we have all the words. So almost stands for this epsilon. Ramanujan means that if I compare it to the spectral radius of the universal cover, then that's what I'm getting. And I should of course add that this is true with high probability, and with high probability stands for this probability going to 0. Okay, I try to break down the adjectives that are there.
Goes to 0 or goes to 1?
Goes to 0 because you really want to say that this is less than that, but you can't say less than that. And so what we managed to do is actually get the same exact theorem. So this is again Bordenave and myself. Same for irregular. So I didn't tell you how to randomly sample an irregular graph, and I'm not going to do that because I don't have the time. But what comes up here is the minimum degree again. So in our case, we have to add TD min here, and it only holds if d min is at least 5. And in these two cases, we have the exact same error. So that's what happens. And the remark I want to add here is that the reason I'm super excited about this is because this is a 100-page paper originally. Now Charles has a more conceptual proof of this 100-page paper, which is only 30 pages, but it's still super technical and very involved. And it's always true it was always true in this setting that the finitary result was much stronger than the infinite result. But in our case, we need the limit theorem. So we need the theorem which works in the limit already to attack this. So it's technically, formally it's true that the finite statement implies the infinite, but we need to use the infinite as a lemma along the way. So really it's a place where the infinite techniques have to complement the very involved techniques from the finite thing to get something nice. It's not like the finite is stronger than the infinite. Okay. Thank you for your attention.
Okay, I'll go first. I have a kind of vague question, which is how are these two statements related? So
what do you mean? This one and that one?
Yeah. Is there a way to describe that?
So I didn't say what a random irregular graph is, because I ran out of time. It's sampled using something called the configuration model, and that will be locally tree-like. So the Benjamin-Ishram limit will be the unimodular Galton-Watson tree. That's how they are related on the nose, and it's kind of an obvious thing that if you had, so if you had a vector here which would prove to you that the spectral radius is larger than what it should be, then you could put that on the finite random graphs, and then you would get higher spectral radius there. So the finite implying the infinite is kind of clear. It's a two-line argument or something like that. And in the case of the regular tree, there really this proof of Friedman doesn't use anything about limits. It's just very concrete techniques. But and I also, just one more remark is that so even with the infinite result, this is not easy. It's not a straightforward generalization of there are quite a few new ideas that you have to put in it, but you know, Charles is very well versed in this. So it's his topic. He has a lot of tools that he built up, and one has to use quite a few of those tools that he built up, also compared to his 30-page paper. So I don't know how long this will be when we write it up, but this is still hard. But the reason I'm very excited about it is because you can very cleanly separate the infinite statement, and that's already interesting. It's sorry, very long answer.
Is there anything special about number 5?
Not really. What I can say is that somehow to prove this, we have to look at random walks on regular trees, and we have to ask if they regenerate or not. By regenerate, I mean they use an edge only once and stay on the other side forever. And you try to compare the exponential decay rate of the probability that you have no such regeneration, and you try to compare it to the spectral radius, which is the exponential decay rate of actually returning to zero. And somehow, if d is at least 5, then the two exponential decay rates are the same. At least I can prove that they are the same, and in the other two cases, I cannot prove that they are the same. The best bound I can get is like this. Maybe they are the same. I'm not ruling it out, but we can prove. So that's an open question. You seem like you're interested.
Speaking about exponential decay, this is exactly what we get in the Friedmans and the other. The convergence material in terms of epsilon, it is exponential.
I'm probably, yes.
Would a result like this be useful, like quantitative, you know?
I don't know. To be honest, I don't know. I never thought that. But I guess. And I guess it should be exponential.
I mean, it does sound.
I don't know.
Yeah.
That's not. I'm not exactly sure at the moment. I would rather not say.
No more questions, then thank you, okay?